Hi, I'm here with Amelia,
Hello.
and we are talking about some applications of log problems. So two applications here. One is how we measure sound. It's called the decibel scale. And two is how we measure the brightness of stars and planets and the moon, etc. That's called the apparent magnitude. So as far as the decibel scale for sound, maybe you can hear my 3-year-old son in the background too. He's pretty excited at life. Let's see. D equals 10 log, that's implicitly log base 10 of E over E naught, where D is the decibels, E is the sound intensity, and E naught is the intensity of the quietest sound typical human ears can hear. Okay, so here's an example problem. If you whisper at 15 decibels, and normally you speak at 70 decibels, say something normal.
Normal.
How many times louder is your regular voice than your whisper? Okay, well, so maybe we ought to start with this equation, okay? And normal whispering, maybe we ought to write that as EW for whisper. And that's going to be 15 decimals. So the decibel level is 15, okay? But then we could also say, well, we got another equation. What about regular sound? Okay, well, regular sound, regular talking, in this example is 70. Maybe you talk at 60 because you're really quiet and proper or whatnot. Okay, so there's two ways to approach this problem. One way is you could solve this. This is a log equation, divide by 10, make it an exponential equation, make this an exponential equation, and try to get ER over EW. That's telling you how much louder the sound waves from your regular voice are compared to the sound waves of your whisper. But I think what they're looking for, remember this is in a section talking about log properties, so say subtracting logs, is what if you subtracted, you need ER over EW. What if we subtracted the right side of this from the right side of that, the left side of this from the left side of that, and let's see what we got. So 70 minus 15 on the left, and 10 log ER, maybe I should have pasted this, over E naught, minus, I'll paste the other one, this. Now, we have something here that you can easily use that difference property of logs. Now, I say easily, that 10 is really getting in the way. I think I'm going to divide everything by 10. But you could also change that and make it an exponent. So let's see. I'll take the liberty of doing two things in the same step. 70 minus 15 is 55. Then we'll divide everything in sight by 10. So I have this, divided everything by 10. Now you can see I've just got those logs together and I can subtract, okay? So how does subtracting work? Remember, if you have the output subtracted, that's the same as dividing the inputs. So how do I write that? Maybe I write it as this divided by e to the w over e naught. Okay, so well, what do you do with that? If you have a fraction within a fraction, you know that you can always simplify it, right? So let's see, what is that? It's ER over EW. Remember, and that's the ratio that I'm actually kind of interested in. I'm interested in what that ratio equals. Now I have a basic log equation. I have 5.5 equals log base 10 of ER over EW. I'm going to convert that into a basic exponential equation. Start with my base, e to the 5.5 equals ER over EW. W. So the question is really how much louder is the sound wave from your regular talking compared to your whisper? And the answer is 10 to the 55 times bigger. So let's go over to Desmos. What's 10 to the 55? Well, 10 squared is 100, 10 to the third is 1,000, 10 to the fifth is 100,000. So we're bigger than 100,000. It's kind of loud, isn't it, Amelia? It's 316,000 times louder. That's a lot louder. And that's why we need a scale. It's hard for us to compare things that are hundreds of thousands of times louder. Or think if you were yelling, it might be 1,000,000 times louder. And so what we do is we use the decibel scale. Apparent magnitude of stars is interesting because often these things get louder. Louder means bigger. Apparent magnitude of stars, brighter actually means smaller. Okay, so this is how it works. M equals 5/2 log base 10 of B naught over B. So notice the B is in the denominator, which means as it gets bigger, M gets smaller. Where M is the magnitude, B is the brightness of the object, and B naught is set so Polaris, the North Star, has a magnitude of approximately 2. Jupiter has an apparent magnitude of negative 2.2. What's the apparent magnitude of a star twice as bright as Jupiter? Okay, so look, I've taken the liberty of plugging in negative 2.2 for M and BJ for Jupiter. Okay, and by the way, it might be interesting for you to fiddle and like plug in what happens if you put in B naught here. Yeah, just have a look. Should be interesting. You better get out too, right? So let's see. So what do we do? Well, this problem says, and this isn't interesting. This again is dealing with algebra related to logs. It's saying, this isn't the only way to do it, but they're saying, I need to know, hey, what is the brightness if I had something that's twice as bright as Jupiter there? Okay, I really want to know what's over here. Okay, so what we're going to do is we're going to take this top equation and we're going to do something creative to it, getting it in the right way. And this is an important calculus technique. When you need to have a 2 there, well, I can certainly put a 2 there. The question is at what cost? And the answer is I have to have a 2 on the top. Okay, well, it's all well and good to have a 2 on the top, except for I don't want a 2 on the top at the end. How do I not get a 2 on the top at the end? Answer, I use the log properties. Shocking, I know. So that 2, how do you get rid of a 2 in the numerator? Well, 2 times something in the numerator is actually log base 2 plus that other something. Notice what I'm doing is I start with the equation I have, right? This was the equation I have. I just filled in the stuff. I figured out where I wanted to end up. I need to end up with B naught over twice as bright as Jupiter. Twice as bright as Jupiter was my goal, right? And so I'm getting closer to this number. But what do I do now? Well, this is what I want. I'll distribute the 5/2. And what I, yes, Tim? You can certainly. I'm afraid the allure of apparent brightness may have decreased over time. Okay, so whoops, that wasn't what I was trying for. Let's see, what do I want? I need that piece. Plus 5/2. 5/2 of that. Okay, so I'm trying to solve for how much that is. This is actually just an algebraic piece, so I'm going to subtract it over to the other side. I mentioned, now you might say, why is it negative? Because brighter is smaller. This is actually, Jupiter is brighter than the North Star, so it's a negative magnitude. And now what we're going to do is I'm going to subtract that over to the other side, and you'll see that, in fact, something that is brighter than Jupiter is less than 2.2. Let's see, negative 2.2 minus 5/2. Go over to our trusty Desmos. Negative 2.2 minus 5/2 log of 2. Is negative 2.95. There you have it, folks. Something that's twice as bright. The log scale doesn't say it's like double that number. It's negative 2.59 apparent magnitude. Okay, hope these were helpful, and I will be happy to answer questions in class if you like that.